All right. So today, I need to take my headphones off. This is loud in my ears. We're gonna finish up determinants, and we're gonna get into vector spaces. So there's only like a couple of things that we need to cover about determinants that we didn't cover in the last lecture, and then we're gonna move on to vector spaces, and those have subspaces. So it'll be very familiar territory, I think. So the one thing we talked about was if you do have a upper triangular matrix, which just remember that meant like you had number, and then eventually it was along the diagonal. These were all some number, and then everything below this was zeros. And then above, it didn't really matter. All that mattered above was that they were just some numbers. But the important thing was everything on the main diagonal, or everything below the main diagonal, was a zero. And if you did that, the way determinants work and doing the cofactor expansion, then you found the determinant was simply just multiply everything along that diagonal. Now you can have an upper triangular or a lower triangular. Key thing is just it's one of those two. So the thing that we didn't get to was, well, what if I start doing row operations? That's where you have to be careful, because if you do row operations, you have to keep in mind what happened along the way. So if, for example, you're in the middle of doing a determinant and you go, oh, it would be better if row 3 was row 1, and you swap those two, all you have to do is just throw a negative out front. And that basically, well, counteracts it. It gives you the same determinant as if you had just calculated it originally. Now, if you multiply a row by some number alpha to get the matrix C, then that constant that you multiplied by times the determinant of A is the same as the determinant of C. So you can go through, you can find all these things, and it makes them pretty easy to go forth about. Now, the nice thing, and this is the best part, if you do a row replacement, so like when we were, like if you think about trying to get something in reduced echelon form, or just simply echelon form. So like whenever we said, okay, along the diagonal, like your 1 1, your 2 2, up to n, however the size of the matrix is, if you don't swap any rows, you don't multiply anything by a constant, then the nice thing is the determinant of the matrix you start with, as long as you just continue to do those elementary row operations, or I should say this, if you do the elementary row operation of adding a row times a constant to another row, that's the nicest one, because then you don't have to do any like counteracting measures. Everything still works the same. So let's take this one for example. And you'll see what I mean by that. Now remember, I'm trying to find the determinant of this matrix. So what I want to try and do is get it in upper triangular, which means I just need to row reduce it to echelon form. Now, I don't want a 0 on the diagonal. Remember, if you have a 0 along the diagonal, that means, well, I should say this. If you have a determinant that is 0, remember the matrix is not invertible. So I would rather have this 0, because I'm trying to get it in echelon form. I want to swap row 3 and row 2. Now, if I do that, that means I'm going up to here. So I swap two rows. So now I've got -1, 3, 1. And then this will be 0, 2, -3. And I left the middle row alone. So I applied that first one. Now I'm not actually going to apply the second one. So this is going to be, if I call this one 3, then we get, I'm just going to add row 1 to row 2. So that's going to give me -1, 3, 1. And so then this would be 0. This would be, if my brain works, this would be -4. And this would be 5. And then we have 0 to -3. Those still don't change. Now, I could either divide the row, or because I want to make this a little bit easier, now I'm going to apply, so this was applying 3. I'm going to apply 1 again. So this will actually be -1 and a -1 to get me -1, 3, 1, and then 0, 2, -3, and 0, -4, 5. So then I can just add, this will be number 3. I'm just going to add 2 times row 3, or sorry, 2 times row 2 to row 3. And the two negatives, I'll get -1 times -1, which when multiplied together gets you 1. I have a math degree. I can't do -1 times 1. So then we get -1, 3, 1, 0, 2, -3, and then 0, 0, and -1. And now, all I have to do to get my determinant is just do -1 times 2 times -1, which is just +2. So this is the nice thing with these. Whenever you go to find the determinant of a matrix, you could do the cofactor expansion. You could do, if it's a 3 by 3, you could do the kind of the shortcuts that we've talked about. But if it's kind of larger, then it may actually just be easier to do those row operations to it to figure out, well, which one is which. So notice up here, we never used 2. Now it says that I should get the same determinant regardless. So notice it says if you multiply row alpha, or a row by alpha to get C, then alpha times the determinant of A should be the same as C. So if you wanted to, you could multiply row 2 by like a half or something like that. And as long as you do a half times the determinant of A, that will get you the determinant of C. So again, it's these counteracting measures. So that covers it for determinants. And next thing we're going to do are vector spaces. And I should silence my phone. So, vector spaces. The most important one is RN. Because think about everything that we've done in linear algebra. It's always been, we talk about a matrix as a collection of vectors. We talk about, typically, we talk about 3D space and stuff like that. Could do 2D space, 4D space, whichever. But RN is going to be our very important one. It is the kind of the crux of what we do in linear algebra most of the time. Everything's dealing with some vectors in Rn. And if you think about a matrix as like a 3 by 3, you can think about that as a collection of vectors from R3. Now, the properties of a vector space are very important, and there's some things that we use a lot, but you might not think about them in this context. So a vector space V is a non-empty set of objects called vectors with two operations defined, called addition of vectors and multiplication by scalars, or real numbers. So we're going to let U, V, and W be our elements of this vector space, and C and D are going to be our constants that will be the scalars. So what are some of these properties? Now the key thing is, though, vector space is a space of vectors. I know that may sound dumb and kind of recursively defining the thing, but a vector space is not just going to be like Rn. So like we're not just going to talk about R4 or R5, R72, whatever. There are other vector spaces that exist. But first, let's define their properties. So if you take, so a vector space has two operations and they must satisfy these 10 axioms. So the 10 axioms are as follows, and they apply to, it doesn't matter if you're talking about a R3 vector, an R4 vector, or some of the other types of vector spaces, they will always obey these rules. So firstly, the sum of two vectors will always be in the vector space. So we say this is closed under addition. So it basically, what it says is if I add two things that are in the space together, I don't magically jump out of the space. So if you talk about vectors that are like R2, you add two R2 vectors together, you don't magically end up in R3. Stuff like that. It doesn't matter the order that I add the vectors in, which is nice. If you go on to take abstract algebra, you'll refer to this as it's abelian, meaning the operation order doesn't matter, or it has a commutative property. So if I take two vectors, it doesn't matter if I do vector 1 plus vector 2 or vector 2 plus vector 1, it's still the same thing. And then with parentheses, it doesn't matter the order that you kind of associate them with the parentheses. You're still going to get the same answer, which is nice because it means if it's easier to do U plus V and then add W, but maybe it was the other way where it was U and then plus V plus W, and that one in parentheses, you can always pick the easier option. And the nice thing is you could use the commutativity property along with the associativity property and say, oh, maybe it's easier if I add the first element and the fifth element at the start. Well, then you can just use the you can use associativity and commutativity together to rearrange them to make it easier. You're always going to have a zero. And that property of the zero is that when you add it to another vector, well, it doesn't change what the vector is. So we think about this as like the zero vector, where if you're like in R4, it's just a zero in each of the 4 available slots. And then each vector that's in your vector space will always have a negative U, such that if you do U plus negative U, you get 0. This has, so every, let me write it down. So basically it means every element has an additive inverse, which means if there's a vector in your space, you can always find another vector that you add it to, and you get the zero vector out. So you're never going to have an element that doesn't have an inverse. So that's what number 5 is saying. If you multiply a vector by a scalar, then that will also be in there. You're never going to have, again, kind of like with adding two vectors together. If you multiply the two vectors together, if you multiply a vector times a scalar, that should still be in the space. You don't get to escape it by multiplying it by a scalar. You can distribute a scalar over parentheses, and you will still get the same result. So again, if it's easier to do u plus v and then multiply by c, or do c times your vector and then do c times your other vector and then add them together, it'll work out either way. So then you can distribute the sum of two scalars over a single vector. Similar idea to the previous, but now instead of distributing over a constant over the sum of two vectors, it's the sum of two constants over a single vector. And this could apply to multiple vectors. If you have, so I'll write this over here. So if you had c plus d times u plus v, that would be c plus d times u plus c plus d times v. So you can distribute them like that, whichever way. And then you could apply scalar distribution if you wanted to these. And then scalar multiplication, it doesn't matter if you do, say you have two scalars that are multiplied, you can multiply one of the scalars first times the vector and then multiply the other scalar, or you can multiply the two scalars together and then multiply them by the vector, whichever is easier for the given scenario. And of course, 10, which I won't say is kind of it sounds obvious, but it's necessary. If you multiply 1 times your vector, you should get back the original vector. It's kind of like a multiplicative identity, but we don't have vector multiplication right now. So we just have to treat it, or you just have to think about the scalar times the vector. So then there's a few important facts that follow. These are not axioms that are defined, but it's just what would follow. So 0 times any vector will give you the 0 vector. And any constant times the 0 vector will give you, again, the 0 vector. And then the third one is something to be aware of. Typically we think about, well, if I just do something plus the negative version of that something, it works out the same way. But you can think of negative u, so a negative vector, as a negative 1 times u. Again, u is a vector, not just a number, so you have to treat it a little bit differently. It's kind of the underlying thing that has worked all the time, but you just don't really think about it too much. So with the examples of vector spaces, or we'll go on now to some examples of what are some vector spaces. So like I said, the most important one and the one that we use most of the time here is Rn. And Rn can be 2 by 2, or not a 2 by 2, sorry. It can be, you can have 2 entries, 3. N has just got to be finite for this. There are infinite dimensional vector spaces, but right now we're just sticking with finite. So then think about R2 by 2. So this is the set of all 2 by 2 matrices. So in this vector space, our 0 vector, and again, you have to think about it as this is a 0 of the space. And the 0 of the space should be, what do I add to my elements in the space such that I don't change them? So if you're dealing with a 2 by 2 vector, or sorry, a 2 by 2 matrix, then I should just have to add a matrix of all zeros, and that will not change any entries. So this is what the 0 is for your 2 by 2 matrices. And so then the next one would be our m by n. So m rows with n columns. And again, we're talking about strictly addition and a scalar multiplication. We know that if you try and you can't find an inverse of a square matrix, or you can only find the inverse of a square matrix. But every matrix should have an additive inverse. It should just be change the signs of every one of those vectors, or every one of the entries, sorry. So this is another example. Now this one's a little bit different. This is a vector space. It just doesn't look like it at first. So p of x, where p is a polynomial and the degree is less than or equal to n. The answer is yes. And so in this space, your 0 vector, well, before we talk about what the 0 vector is, what do the elements of this space look like? So anything in here is going to be, again, it's a polynomial. So go back to that definition. Whole numbers for your exponents times real coefficients. So we have an times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and this would continue onward. And then we'd eventually get down to a2x squared plus a1x, and then just plus a0. And then all of your a's are some real number. So it doesn't matter which one of these you pick, it's still going to be in there. So in this case, my 0 you can think about it as just doing 0 times x to the n plus 0 times x to the n minus 1, so on and so forth. Which in this case, your 0 is literally 0. Because if you add it to any polynomial, then the value won't change. You'll still have whatever the polynomial was that you started with. And again, these will be closed under that addition rule, because you can add two n degree polynomials together, and you're not all of a sudden going to get an n plus 1. You can only decrease the degree, you can't increase it from the from the given components. That's why it specifically says less than or equal to n and not equal to n. Because if you said it had to be equal to n, nothing has inverses. If I do x to the n plus negative x to the n, I get 0, which is degree 0. or even if I do x to the n plus 2x plus negative x to the n, I'll get 2x, and that has a degree of 1. So you can always decrease the degree. But the thing is, it's very specific on the degree is going to be less than or equal to n. Not that the degree has to be equal to n. Because if you make it equal, then it's not a vector space because the inverses break the rule. So the 0 or you can never actually have 0 in there. Now this one's a really weirdly specific one. So p of x is a polynomial in Pn, and P1 is equal to P5, which is equal to P17, which equals 0. As strange as it is, yes. Because all this is, if you think about it, is it's a subset of the first one. The only difference is this one has to have the roots of 1, 5, and 17. Now, it doesn't say what the multiplicities have to be, but you can basically think about this as like if you had x minus 1 to the k sub 1 times x minus 5 to the k sub 2, x minus 17 to the k sub 3, and then times some, I won't come up with a proper representation, but we'll just say, we'll call it p prime of x. Not that it's the derivative, but just that it's some other components. And specifically that the degree is less than or equal to n. So whatever the polynomial is, it's still going to have a degree that's less than or equal to n. The only thing is this one has specified that you have roots of 1, 5, and 17. It's still going to, if you add two things that have those roots together, you still keep it, all that kind of stuff. You do have a 0, which is still going to be 0, but it might just be 0 times x minus 1, x minus 5, x minus 17, like that. So these are some examples that we have. So what are some that are not in our textbook that we use? So if I take the set of all infinite sequences, so remember an infinite sequence is going to be just a0, a1, a2, so on and so forth, and the answer is going to be yes, because they're sequences. So if I put them together, I just get a new sequence that's still infinite, and all the rules would still apply. And then let's say you take this one, L1. Now this is a very kind of specific sequence, but what it is all of your sequences, if I add the absolute value of the terms in the sequence together, it stays finite. And the answer to that one, also yes. Because if you add two things that are less than infinity together, they're still going to be less than infinity, which is kind of nice. The set of all functions that are differentiable on the interval AB. That's also going to be, because if you add two differentiable functions together, they stay differentiable. You don't add two things that are not different, or that are, you don't add two things that are differentiable and then suddenly you can't differentiate them anymore. This is a very specific one. So it's the set of functions whose first and second derivative, or it's, let me rephrase that. Basically, the first derivative, the second derivative, and the original function all have derivatives, which means basically, do you have a function that's 3 times differentiable? And again, that's also going to be a vector space. And with these, you can go and you can try the different rules. You can say, okay, well, what if I try like, you could try x to the 5th. That has 3 derivatives. You could try sine of x. That's differentiable 3 times. And then you could try like adding them together and moving them around, stuff like that, using those rules. L of AB, which means it's the set of integrals such that when I do the integration of them, they have a finite integral. So remember, integral is just the area under the curve. So it's all the functions that have a finite amount of area under the curve on a given interval. So you could take a function that has an infinite amount of area, but if you chop it at a certain point, it could be finite. And then again, you add 2 things that are finite, you still get finite. And then a slight variation, the L2 vector space. Again, yes and yes. These both meet the conditions. The second one's just a very, again, it's kind of like a more specific version. You just throw those different boundaries on it. So these are all vector spaces that can come up. Now for us, again, most of the time we're going to deal with vectors, matrices, stuff like that. But seeing these are very important to just kind of also get the context of vector spaces show up in other branches of mathematics and not just our linear algebra course. So with that out of the way, we can actually kind of do some things with them and kind of see what you can and can't do with vector spaces. So we can go back to kind of a subspace idea. So think about a subspace as kind of like a very specific subset. It has a few rules. So a vector space can be a subspace if 0 is in there. If you add 2 vectors in the subspace together, you stay in that subspace. And if you multiply by a constant, something that's in the subspace, you stay in the subspace. So it's kind of like just a narrowed down version of the original thing. Hence why it's a subspace. But notice it's not a subset. There's a big difference. Like if I take, let's say I do the vector A1 and A2, which is in R2, such that A1 and A2 are only positive entries. Then, well, maybe I shouldn't say positive entries. Let's narrow it down to their natural numbers. So if we take something like this, then could that be a subspace? Well, we know at the very least it's a subset. You can always take a subset, but not every subset is going to be a subspace. So first thing, if I do I have 0? Yeah. It's equal to just 0, 0, because 0 is a natural number. Well, let's change it to integers just so we don't step on any toes. Because 0 is technically, natural number is counting numbers. So 1, 2, 3, 4, 5, so on and so forth. So let me make this a little bit more specific. Can I add two things together and stay in the subspace? Yeah, it doesn't matter if I add two integers together. I'm still going to get an integer. The problem is, though, let's take any element. Let's just say I do, for number 3, let's say I do 2, 1. And I multiply it by a half. Well, now I have 1 and then 1/2, which is not in our subspace H. So this one breaks the rule in a very particular way. And that particular way is it fails the constant or the scalar multiple check. If we could have multiplied any constant and still stayed in the space, then we would have been okay. But again, for all of the values of A, which means I can pick any constant, if you find one that doesn't work, then the whole thing fails. So let me erase that. So you always have the trivial subspaces, which are just your 0 vector and the whole space itself. And of course you might be able to find some other ones, but if you are just in doubt of what are two subspaces, then all you have to simply do is just say just the 0 vector and the whole space itself. So is H, which is P of X, such that P of 1 equals 0, a subspace of P sub n? So like before, what this is saying is, can I do basically x minus 1 to the k and then multiply it by something else and get, we can call it like P prime of X. Well, yeah. Because if I add two things together that have a root of 0, like let's say, or that have 1 as a root, well, is 0 in there? Yes, because if your vector is 0, then technically everything is a root, because it doesn't matter what you plug in for x, you always get 0. So at the very least, it passes 1. What about 2? I'm going to have to do 2 up here. If I have x minus 1 to the k1 times P prime of X plus x minus 1 to the k2 times Q prime of X, or Q star, I'll use, then you can see if I add them together, they both still have a root of x minus 1. They both have at least 1. So I don't know exactly how many of them I could pull out as a root, but I know I could pull out at least 1. So the key thing would be they still have a root of 1. So yes. And then if you use the same idea, think about it. If you multiply a polynomial by a scalar, you don't change the value of the roots. If you have x minus 30 times x plus 42, it doesn't matter if I multiply 1,000 out front. They still have the same roots. So for number 3, it also would pass. So that's one example. What about this one? So this is basically a 3x3 matrix such that the first row and the third column have all 0 entries. Is that a subspace? So if we talk about 1, 2, and 3. So is the 0 vector in there? Yes. I would just make A, B, C, and D all 0. If I add 2 of them together, let's get messy for a second. So 0, 0, 0. And I'm going to call this A1, B1, 0, C1, D1, 0, plus 0, 0, 0, A2, B2, 0, C2, D2, 0. And then, of course, if you add those together, you have A1 plus B, or A1 plus A2, B1 plus B2, C1 plus C2, and whoops, we don't need a second row of B's. We get D1 plus D2, and then 0, 0, 0, 0, and 0 again, which is still in the subspace because those 4 entries are still just some real number. Doesn't matter. They're still in there. And then 3, also pretty easy. It's just going to be 0, 0, 0. And, well, we can't use A, but let's just say, and you can't use C either. Dang it. I didn't think this one through. We'll just use Z. So you'd have Z times A, Z times B, 0, Z times C, and Z times D, and then another 0. And so this would also be a yes. The key thing for checking a subspace is the 0 vector in there? And again, it's the 0 vector of your particular space, not just is 0 in there. Because 0 for the polynomial space looks very different from the 0 for a matrix space. So you have to make sure that the 0 of that vector space is in there. And typically that's one of the first things you want to try and do is just say, okay, well, there's 0 in there. Because when you're checking for vector spaces, if 0 is not in there, that's just an easy way to knock out the fact that it's not a vector space. So those are a couple examples. Now, we've talked about span before, but what does that mean in terms of a vector space? Still going to be very similar. So if V1, V2 through Vn are vectors in your vector space V, then the span is just what are all the linear combinations of those. So some constant times V1 plus another constant times V2, blah, 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 up to An times Vn. So your span will be all the possible linear combinations of your vectors. And then this is a nice one. If you have V1 through V2, or sorry, V1 through Vn that are in your vector space, then the span of those vectors is a subspace. Because Remember we said that basically they were closed under, if you add two vectors together in the space, you stayed in the space. If you multiplied a constant times a vector in the space, you stayed in the space. And then you could add a vector times a scalar and still stay, or a vector times a scalar plus another vector times a scalar, and you stay in the space. So kind of meeting that default of the linear combination part. So our 1x and x squared in L squared 0, 1. So if we go, so remember, this is the space of vectors such that what this is going to be is the set of functions such that the integral from 0 to 1, the absolute value of f of x, is going to be finite. So in this case, what I'm saying is, if I were to try and use those vectors, would they be in there? And the answer would be yeah, because I can do this as 1 times a1 plus, or I should swap the order of these. If I do a1 times 1 plus a2 times x plus a3 times x squared, then the answer is yes, they will always be in there, because all the scalars are going to do is just, again, it's going to affect how large it will get. But the thing is, on 0 to 1, the integral of 1x and x squared are still going to be a finite value. And it doesn't matter how much stuff you add together that's finite, it never goes infinite. That's the nice thing with these. I mean, clearly, if you add 1 plus 2 plus 3 plus 4, yeah, that's an infinite sum that is infinity. But if you add a finite number of finite things together, it will never be infinity. So is the span 1x and x squared a subspace? So go back to the definition. We just said if they're in there and they're elements, then any linear combination of them will be in that subspace. So the answer to that would also be, can't write with an eraser, would also be yes. Because, to go back for a brief moment, if you let all the constants be 0, it stays in there. If you just change the constants and add them together, that would also be in there. So what I mean by that is, if I take a1, this is why I should have not written them that way, but you know what? It'll work still. a1 plus a2 x, a3, that one should be the x squared. Let me stop being dumb. And then if I added to it b1 times 1 plus b2 times x plus b3 times x squared, then that's still going to give me some form of a constant times 1 plus a constant times x plus a constant times x squared. So adding those two things together will still get me some thing that's in the subspace, or something that's still a form of, like I said, constant times 1 plus constant times x plus constant times x squared. And then, of course, if I had some constant c, times this. Didn't screw up that time. Then that still gives me a constant times 1 plus a constant times x plus a constant times x squared. So I still have something that's in that span. So the answer is still yes. And it's just two ways of checking. Do you want to go through the 3 steps, or if you can show that all of them are elements of the space, which of course they would have to be elements, then the span of those will stay in there and thus will be a subspace. And again, you don't add the things together and then go through and check. Or sorry, I didn't say that part well. You don't add these things together and somehow end up with you don't add these things together and you jump out of the space. If that happens, then you're not in the span. Or sorry, you're not a subspace. You're a subset, but not a subspace. So just keep that in mind, what it means here. And technically, what I should be checking for these is still if I do the integral. But the thing is, like I said before, the integral of x squared and a constant are still going to be finite on 0 to 1. All the constants that are out front just change. Is it a larger value? Is it a smaller value? That's all they're going to change, but they're never going to make it infinite. And that's the key thing. And of course, I wrote over this, but we already talked about the span. The span was this. So we've already addressed what the span is. All right, and that does it for this section. We just did the brief kind of stop in this course for vector spaces. We'll pick up next time with eigenvalues. And y'all have a good rest of the day. And of course, I'm going to save these because I did all that work.